All right, strap yourselves in because today we're going to take a deep dive into the world of cryptography.
Ooh, sounds exciting.
Yeah, breaking down all those must-know cryptographic applications you need to ace that CCSP exam.
Yeah.
Studying for these cybersecurity certs, it can be a bit like drinking from a fire hose.
Right? Tell me about it. It's a lot to take in.
Yeah, totally. So we're here to break it all down, make it easy to digest.
Yeah.
So for this deep dive, you sent us a file, ccsp-d2-5.cryptographicapplications.txt. Looks like a gold mine of info.
That's a good one. Yeah, that file covers some really critical concepts. Understanding those cryptographic applications is like the secret sauce to passing the CCSP. Why is that, you might ask?
Why is that?
Well, think about it. Secure communication, protecting your data, making sure you're talking to the right person. All of that boils down to strong cryptography. We're talking about the foundation of cloud security here. The CCSP exam really wants to see that you can not only define these concepts, but actually put them into practice in real-world cloud environments.
Okay, so it's not just about knowing the theory, it's about being able to actually apply it. Gotcha. So where do we even begin with all of this?
Great question. Let's start with the cornerstone of secure communication, TLS transport layer security. You've probably seen that little lock icon next to website URLs in your browser. That's TLS doing its thing.
Oh yeah, TLS. I see it everywhere. But then there's also this thing called SSL that pops up every now and then. What's the connection between those two?
Good catch. You're right. SSL, or Secure Sockets Layer, it's basically the precursor to TLS. Well, similar in a lot of ways, but SSL has, let's say, a few too many vulnerabilities. We kind of don't talk about it much anymore.
Like that embarrassing relative everyone tries to avoid at family gatherings.
Exactly. TLS is the upgraded, more secure version that everyone has switched to, and you can bet the CCSP exam might try to sneak in some SSL terms just to see if you're paying attention.
Oh, sneaky. So TLS is the gold standard.
Yeah.
Now, before we get too far, what about those digital certificates we always hear about? Where do they fit into this whole thing?
Digital certificates. Those are like digital passports for websites. You wouldn't travel to another country without your passport, right? It proves who you are. Same idea with websites. They use these digital certificates to prove their identity to your browser.
So it's like making sure I'm actually talking to my bank's website and not some scammer trying to steal my money.
Precisely. These certificates are issued by trusted organizations called certificate authorities, CAs. They're like the digital notary verifying that the website is legit.
Okay, starting to make sense now.
Yeah.
But how does TLS actually use these certificates to secure communication?
This is where the TLS handshake comes into play. It's a series of steps the client, your browser, and the server, the website, go through to establish a secure connection.
Okay, I'm picturing a secret handshake. What actually happens during this handshake?
Imagine you want to visit a secure website. Your browser sends a hello message to the server saying, hey, want to chat securely. It also includes a list of cipher suites. These are basically the encryption algorithms it understands.
So it's like saying, here are the security protocols I speak. Can we find some common ground?
Exactly. The server checks its own list and picks the strongest cipher suite they both support. Then it sends back its digital certificate, like saying, here's my ID proof that I am who I say I am.
And my browser checks that ID against its list of trusted certificate authorities to make sure everything's on the up and up.
You got it. Now, both sides have agreed on a common language for encryption and verified each other's identity. What happens next is where things get really interesting.
Ooh, I love a good plot twist. Tell me more.
The browser needs to generate a unique key, a session key that's only used for this particular conversation. It's like a secret code just between you and the server.
So it's like coming up with a secret handshake that only we know.
Perfect analogy. But here's the challenge. How does the browser securely share this secret session key with the server without anyone else intercepting it? That's the tricky part.
Yeah, that does seem like a problem.
And this is where public key cryptography comes in. The browser encrypts that session key using the server's public key. Remember, that was included in the digital certificate. This ensures that only the server with its corresponding private key can decrypt and unlock that secret session key.
It's like sending that secret code in a locked box that only the server has a key to open.
You got it. And once both sides have that shared session key, they can finally start talking securely. All data is encrypted using that key, making it unreadable to anyone snooping around.
This TLS handshake is pretty slick. What happens when we're done chatting? Does that session key just hang around?
Nope. This is where the idea of forward secrecy comes in. When the conversation ends, the session key is destroyed. Poof, gone. Even if someone recorded the whole conversation and somehow got the server's private key later, they still couldn't decrypt anything because that unique key is gone.
Like a self-destructing message? I'm starting to see why understanding this TLS handshake is so important for the CCSP exam.
Absolutely. The exam loves to test those little details of the process. Knowing the steps, the components, and the reason behind each step is super important.
All right. TLS handshake, digital certificates, cipher suites. Got it. But before we get too lost in the TLS weeds, let's move on to another big player in secure communications. So we covered TLS, but I know there's another big player in the security world, IPsec. It sounds kind of like a secret code name or something.
Yeah, a bit mysterious, right?
Yeah.
It's not quite as dramatic as a spy movie, but it's definitely essential for keeping those network communications secure. You see, back in the early days of the internet, security wasn't exactly top of mind.
I can't even imagine a world without internet security these days. It'd be like leaving your front door wide open all the time.
You're telling me. So as the internet grew and we started realizing, hey, we need to protect all this stuff, IPsec came along to add that much needed security. It stands for Internet Protocol Security, and basically it adds those security measures right into the core TCP/IP protocols.
So it's like retrofitting an old house with a state-of-the-art security system. Makes sense. But we were just talking about TLS for secure communication. How's IPsec different?
Great question. They both handle security, but they work at different levels. Remember, TLS focuses on the application layer, like securing web browsing or email. IPsec goes deeper. It works at the network layer, protecting the entire data packet as it travels across the network.
So TLS is like securing the conversation itself, and IPsec is like encrypting the entire package being delivered, no matter what's inside.
Exactly. It's all about securing different parts of the communication process. Now, within IPsec, we have two main protocols that team up to provide that comprehensive security, ESP and AH.
ESP and AH, they sound like a dynamic duo. What are their special skills?
Think of ESP encapsulating security payload as the master of disguise. Its job is to encrypt the data, making sure only the intended recipient can read it. It's like putting that sensitive info in a secret code that only the authorized party can crack.
Okay, so ESP keeps things confidential. What about AH? What's its role in this security team?
AH, authentication header, is all about integrity. It's like a tamper-proof seal verifying that the data hasn't been messed with during transit. Think of sending a really important document. AH makes sure nobody's tampered with it or changed the delivery instructions along the way.
So ESP for confidentiality, AH for integrity, working together to create this super secure tunnel for data.
Right? Precisely. They're the guardians of network security, making sure your data stays both secret and intact. And to make this whole system work seamlessly, we have something called security associations.
ASAs.
Security associations sounds kind of like a dating service for encryption protocols.
Haha, not a bad analogy. Actually, it's about compatibility. You have two systems that want to communicate securely using IPsec. They need to agree on a few key things: which encryption algorithms to use, how to authenticate each other, what keys to use for encryption and decryption.
So it's like making sure they're both speaking the same language of security. Exactly. These agreed upon parameters, that's what makes up a security association. Each system shares a list of what they support, and they choose the strongest, most compatible options they both have in common. It's all about finding that perfect match for the highest level of security.
Makes sense. Got to speak the same language. Now, I know we briefly touched on IPsec VPNs earlier. Can you remind me what those are and how they relate to all this?
Sure, a VPN virtual private network is basically a secure tunnel through the internet. And IPsec is often used to build those tunnels. It's like creating this private, encrypted pathway for your data, even when you're on a public network like the internet.
So it's like having my own personal secret passageway through the internet, safe from prying eyes.
You got it. And with IPsec VPNs, there are two main modes to keep in mind: tunnel mode and transport mode. Different ways of securing that data tunnel.
Okay, break it down for me. What's the difference?
Imagine you have two offices in different cities that need to connect securely. Tunnel mode is like building a secure tunnel between those entire networks. All traffic between them is encapsulated in this encrypted tunnel. It's like they're on the same local network, seamless for users, but with strong security behind the scenes.
So tunnel mode connects whole sites. What about transport mode?
Transport mode focuses on individual devices. It adds encryption to the data traveling between your device and a remote network, but it doesn't encrypt the whole packet header.
So if I'm working from a coffee shop and want to connect securely to my company's network, that's transport mode.
Exactly. But nowadays, transport mode is less common, especially for individuals. Thanks to those user-friendly TLS-based VPNs we talked about earlier, there's often an easier, more efficient way to secure individual connections.
Makes sense. No need to overcomplicate things. So to recap, IPsec secures the whole data packet, uses ESP and AH for confidentiality, and integrity relies on those security associations to find compatible encryption. and is often used to create secure VPN tunnels. We've covered a lot,
Hmm.
but I feel like this is just the tip of the iceberg. What's next on our cryptographic adventure?
Oh.
Okay, so we've explored all the ins and outs of TLS and IPsec, but I feel like we're just scratching the surface here. What about all those other protocols we use every day without even thinking about it? How do we make sure they're not leaving our data exposed in the cloud?
Oh, that's a huge piece of the puzzle. And it's something the CCSP exam really dives into. You got to know how to secure those everyday protocols, the ones that people often overlook, but they can be a real security risk if they're not protected properly.
Right, it's all about the details. So what are some of those protocols we need to keep an eye on?
Let's start with a classic example that everyone can relate to, HTTP versus HTTPS. You know, that little S at the end of HTTPS. That little guy makes all the difference.
I have a feeling it's more than just a letter. What's the big deal about that S?
It stands for secure, meaning the website's using TLS to encrypt the communication between your browser and the server. It's like putting a protective shield around your data as it travels all over the internet.
So instead of sending sensitive info like my credit card details in plain text for anyone to see, HTTPS scrambles it up, makes it unreadable to anyone trying to snoop.
Exactly. And you know what? Most websites these days automatically redirect you to HTTPS, which is a huge win for security overall. But it wasn't always like this. It took a lot of effort and advocacy to get to this point. It's a good reminder that security best practices are always evolving.
Yeah, good point. Now, what about SSH? I know it's used for remote access to servers, but how does it actually guarantee that the connection is secure?
SSH Secure Shell. It's basically the secure replacement for Telnet, which, let's just say, wasn't exactly known for its security. SSH is widely used for remote administration of systems, usually Linux or Unix servers. And it uses that same public key cryptography we talked about earlier to keep things locked down.
So instead of sending commands in plain text, which would be like shouting my passwords across a crowded room, SSH encrypts everything. Keeps those commands and any sensitive info hidden from prying eyes.
Exactly. It's like having your own private secure channel to talk to your server. And just like with TLS, SSH uses that public key cryptography to exchange a session key, so only the authorized user and the server have the key to unlock the communication.
Makes sense. Now, when it comes to sharing files securely, you mentioned FTPS, SFTP, and SCP. Can you break those down for me?
Sure, FTPS. It's basically FTP with an added layer of security. It uses TLS to encrypt the data transfer, so those files are protected while they're on the move. SFTP Secure FTP takes a different approach, uses the SSH protocol for secure file transfer. And then there's SCP Secure Copy. It's a command line tool that also relies on SSH to securely copy files between systems.
Got it. So multiple ways to share files securely, each with its own strengths and use cases. But you also mentioned TFTP. Is that another option we should be thinking about?
TFTP, Trivial File Transfer Protocol. That's one you'll probably see on the CCSP exam. But not because it's a good choice for secure file transfer. Actually, it's quite the opposite. TFTP is known for its lack of security features. It sends data in plain text, which makes it super vulnerable to attacks. So if you see TFTP on the exam, red flags should be going off.
Duly noted. Okay, so we've got secure web traffic, remote access, and file transfer covered. What other everyday protocols need that extra layer of security?
Think about all the different ways we communicate and share info online. Voice and video calls, time synchronization, email, DNS lookups. The list goes on and on.
So many potential weak points if we're not careful.
Exactly. That's why it's crucial to understand how to secure these protocols in a cloud environment. Like instead of using standard NTP for time sync, which can be manipulated, we have NTPsec, which is built with security as a top priority. And for voice and video calls, we can use TLS for things like secure teleconferencing or SRTP for VoIP.
What about email? Seems like email's been around forever. Are there even secure options for something that old?
Of course, instead of those older, less secure email protocols like POP3 and IMAP, we now have their more secure versions, POP3S and IMAPs. They use TLS to encrypt the communication between your email client and the server. And for sending email, we can use SMTPS instead of plain old SMTP, which also uses TLS to secure the connection. And on top of that, you can encrypt the email message itself and any attachments using SMI.
Wow, so many acronyms. That's like learning a whole new language.
It is kind of like that. But once you grasp those underlying concepts, it starts to make a lot more sense. And don't forget about DNSSEC. It helps protect those crucial DNS lookups that connect us to websites and online services. Make sure they haven't been tampered with so we don't end up on some shady imposter site.
I gotta avoid those fake websites. You also mentioned securing DHCP and LDAC. Could you refresh my memory on what those are all about?
Of course, DHCP Dynamic Host Configuration Protocol. It's responsible for automatically assigning IP addresses to devices on a network. Securing DHCP means making sure that only authorized servers can handle those assignments. And then there's LDAP Lightweight Directory Access Protocol. It's used for managing directory services like user accounts and permissions. Thankfully, we have LDAPS, the secure version of LDAP, which uses TLS to encrypt the communication.
Wow. We've covered a ton of ground today, from the nitty-gritty of the TLS handshake to all those everyday protocols we often take for granted. Any final words of wisdom for our listeners as they gear up for the CCSP exam?
Remember, it's not just about memorizing all these protocols and acronyms. It's about understanding how they work, why they matter, and how they all fit into the bigger picture of cloud security. Visualize those handshakes, those encrypted tunnels, those layers of protection. It's about connecting the dots and being able to apply what you've learned to those real-world cloud situations.
Great advice. And here's a final thought-provoking question for everyone out there. With so many of these core internet protocols needing security add-ons, is it time to rethink the internet from the ground up? Should security be baked in from the very beginning instead of being tacked on as an afterthought? Something to ponder on your journey to CCSP mastery.
That's a brilliant question, and one that cybersecurity experts are grappling with right now. It really highlights how important it is to keep innovating and to be proactive about security in this constantly changing digital landscape.
Absolutely. Well, thanks for joining us on this deep dive into the fascinating world of cryptographic applications. Until next time, stay curious, stay secure, and keep learning.